may be guided with some theoretical considerations. So with that, we have finished our job, so let's review. I've looked at the evaluation of fugacities here for pure gases. I expressed it this way. From the Ariel-Pitzer equation of state, I've got the result. From Lee and Kessler tables, those are also the result. We're pretty solid ground there. Component in a gas mixture, well, at least for two-component Pitzer gases, we've got the whole story. And here it is, just all laid out. But the general case, when we have any number of components, it gets fairly complicated, but here is what that result looks like. So those are the Pitzer gases of any number of components. But if we want to use the Lewis and Randall rule, then we do this. It's just fugacity is equal to the pure gas fugacity obtained as up here times the mole fraction. But more often than not, that isn't going to work very well. And next we have fugacity of a pure liquid or a solid. It's given by this general equation, which introduced these two new things. Fugacity coefficient of the pure saturated vapor, often close to 1. And this new guy, what do we call him? Pointing factor. And that will be significantly different from 1 only if this pressure difference is large. So usually that's going to be important when we're dealing with high pressure systems. And for a component in a solution, we can write it out this way, where we put a Butch factor into the Lewis and Randall rule, recognizing that that activity coefficient is going to be a function of everything. So remember what that is. That's so a big job is going to be going forward, looking at correlations and evaluations of that, primarily out of phase equilibrium data. Well, remember we pursued looking at the expression of the thermodynamic properties of an ideal solution. When I talk about the thermodynamic properties of the solution, what am I talking about? Well, first of all, fugacity, chemical potential, partial molar volume, partial molar entropy, partial molar enthalpy. That's the list of properties that completely describe any multi-component system. So now we've got a general solution with introduced and described by this Butch factor, the activity coefficient, so we might look at how that works. So let's pursue that for a moment. So what I'm concerned here with is the thermodynamic properties of non-ideal solutions in terms of activity coefficients. So now what I've got is an expression for the chemical potential here, which is the pure component value plus RT times log of the activity. In other words, a modified mole fraction, gamma I times Xi. And that's equal to, as before, just using the fundamental equation. This is a little bit in error, so I can fix this. A little bit crowded there, but you see what I'm writing, d mu I is equal to minus Si, dt plus vi dt. So that's the fundamental equation for it, and that's how we extract the derivatives that we need. So we can go right down the list. First of all, partial molar volume, that's going to be, does everybody see this, by the way? That we go right from here, partial molar, this part? I've built the derivative out of this fundamental equation. But it's important that you see that. Please, if anybody doesn't see it, let me know. We can talk about it more. Yeah, let's talk about it some more then. This, of course, I could write, this is just a free energy quantity. So the original fundamental equation was this. That just goes back to the fundamental equation. Now I can apply that to partial molar quantities, and that means I'm going to turn this thing into mu I, but then I need the corresponding partial molar quantities up here. Is that okay? Okay, so once I've got that, now I can build derivatives out of it. So this is gonna call for, and if I write it all out, I find I don't have space here. Do I dare do something on the board? I don't think lightning will come down and strike me, but.
Good luck with this.
This cleans up very well. It's kind of on there. So if I want to build a derivative, what I'm interested in so I'll just divide through in the usual way. This is just one. Then I'll impose constancy of temperature. Oops. This goes to 0. At constant temperature. Trivially 0, and so all I've got left here is this. So, make sense? So here I've written it all out where d mu I is, now, I'm sorry, mu I itself is equal to this whole thing. So when I differentiate that with respect to pressure, I'm differentiating all of these three terms. I'm splitting mu I and xi apart into separate terms here. And this, the derivative of mu I 0 with respect to pressure, constant temperature, is just vi 0. And then what I have here is RT and partial log m I with respect to P. At constant temperature and composition, this doesn't give me anything, that's just a constant. So this is all I'm left with. That was 0, so this is what I'm left with. Now the partial molar volume of a component in a real solution is equal to its pure component value now plus RT times the pressure derivative of the log of the activity coefficient. So if you get that, the rest of these are going to be just crunch and grind. So SI is going to be minus, because we see we got a minus up there. The chemical potential derivative with respect to temperature, constant pressure, and composition, so indicating that here. I get a few more terms left over for entropy. So this one is going to be your pure component molar entropy minus R log of the activity coefficient minus RT temperature derivative of the log of the activity coefficient. And here we got a T, and I'm differentiating with respect to T, so I have R log xi left there. So the whole thing involves all of these terms. Then for enthalpy, we don't need to do it again because I can put together expressions I've got for Gibbs free energy, which is chemical potential, plus T times the partial molar entropy, and I've just put those terms together, see some simplification goes, and I end up with this expression. So if I put the whole thing together, I end up with a table like this, properties of non-ideal solutions. So now I've got expressions with complete generality for all of the properties, any and all of the properties I might need describing a real or a non-ideal solution. And I can put them together in the usual way to get the molar property changes of mixing, which are important. And you see that they depend on, where this was 0 for the case of an ideal solution, now it isn't 0 anymore. It's going to depend on the nature of the pressure dependence of the log of activity coefficient. Heat of mixing also is not 0 anymore, but I can express it here in terms of temperature derivatives of the logs of the activity coefficient. And entropy, a little bit messier. And of course for the Gibbs free energy change of mixing, here it is. So it should be apparent, looking at this, that if I have knowledge of the activity coefficient as a function of everything it depends on, I would be able to derive any and all of these properties. So what this has done is to essentially codify our ignorance, but at least it's put it now in a single form here, so we know what we need to get in order to be able to proceed further to get actual quantitative descriptions of these things. So I hope that much is understood. And then what we'll start with tomorrow, hopefully, is a look at vapor liquid equilibrium, which is the principal mode with respect to which we can evaluate these properties, that is the activity coefficients. So this was a heavy-duty lecture today. Any questions about it, or things we should clear up before I move on to the next issue, which I'm going to wait till tomorrow to do? Yeah.
For the Lewis-Randall rule,
Yeah.
can you again clarify like when it would hold? 'Cause I know you mentioned the excess part, but that was only for one component that the excess would follow it. But what about for the entire solution, entire mixture?
Well, as a quick answer to your question, it almost never holds.
Okay.
But when we have Raoult's law, with something that can be described by Raoult's law, obviously we're saying it holds. Because that is assumed in it that we have an ideal solution, so Raoult's law assumes that all the gammas are equal to 1. But that is a rare situation.
So is there a way that we can like mathematically check if it holds, or would we just be told that it holds in that case?
Well, we can start looking at, it holds if I've got molecules that are approximately the same size and similar chemically. So we got things like benzene, toluene solutions, that's pretty well described by it. Or if I have like D2O and water solutions, that's very well described by it. And you can think of other cases where I have very similar molecules, then it will be okay. Yeah?
Do they have to be similar in like molecular weight, or does the total mass have to be similar?
Yeah, you want similar molecular weight, because molecular weight goes right along with size.
Okay.
And you start to get, as you could well imagine, if I have a large difference in size, that leads to non-ideality.
Thank you.
Yeah.
Would that be similar structure too? So if that affects solubility?
Yeah. In fact, if the structure gets very far away from being just simple globular, you're in trouble. So the sad truth is that it's a pretty rare case that simple case holds. We're a little bit better off in gas mixtures. And one thing you know is that it will hold for one component by itself if that component is present in excess. And that's across the board. Anything else we can discuss? We got a minute or two here.
Yeah, one quick question. I'm trying to understand the board and the chemical potential. It almost looks like you're equating chemical potential to Gibbs free energy.
I am.
But chemical potential is equal to the partial Gibbs free
Yep.
energy.
So that's the partial molar Gibbs free energy. And therefore, I've
Yeah.
got partial molar things here as well.
Oh, I see the bars now. Okay, super. Makes sense.
Anything else? Well, if there's no other question or discussion, that's it for today.
Take the picture of the board if you don't mind.
Yeah.
Before you erase it.
I finally got the sound